Hello everybody, my name is Iman. Welcome back to my YouTube channel. Today we're going to tackle a practice problem set for chapter 4 of General Chemistry 1. This chapter was titled Types of Chemical Reactions and Solution Stoichiometry. Let's go ahead and get started with our first problem. This first problem reads, calculate the molarity of a solution prepared by dissolving 11.5 grams of solid sodium hydroxide in enough water to make 1.5 liters of solution. Now, our definition for molarity is moles of solute divided by liters of solution. Looking at what we're given in the problem, we're given liters of solution, but we're not given moles of solute. Instead, we're given grams of solute, 11.5 grams of sodium hydroxide. But that's okay because we can easily convert it to moles using molar mass. So let's go ahead and do that. 11.5 grams of sodium hydroxide. We want to use molar mass to convert this to moles of sodium hydroxide. Molar mass of sodium hydroxide is 40 grams per mole. So we're going to write that down. What we notice is that grams of sodium hydroxide cancel out. We're going to get our final answer in moles of sodium hydroxide. Plug this into a calculator. We're going to get 0.288. Now we have moles of solute, we have liters of solution. We can go ahead and calculate molarity. We're going to get 0.288 moles of solute over 1.5 liters of solution. And what this is going to give us, if we plug into a calculator, is 0.192 molar sodium hydroxide. We went ahead and we calculated the molarity. Let's go ahead and move into our second example. Problem 2 reads, to analyze the alcohol content of a certain wine, a chemist needs 1 liter of an aqueous 0.2 molar potassium dichromate solution. How much solid potassium dichromate must be weighed out to make this solution? Okay, so we are given the molarity of the solution. We're given the liters of solution. Technically, using our definition of molarity, we can go ahead and figure out the moles of solute, aka the moles of potassium dichromate. However, this problem asks us for how much solid potassium dichromate must be weighed out. So our final answer needs to be in grams of potassium dichromate. So first we're going to figure out moles, and then we're going to convert moles of potassium dichromate to grams in order to solve the problem. So let's go ahead and do just that. We know our molarity and we know our liters of solution, so we can solve moles of solute by moving liters of solution over to the other side, multiplying that by molarity. So what this looks like is 1 liter solution multiplied by 0.2 molar potassium dichromate, which looks like 0.2 moles over 1 liter solution. Liters of solution cancel out, and we get our moles of potassium dichromate to be 0.200 moles of potassium dichromate. Okay, now that we have moles of potassium dichromate, we can figure out grams by converting using molar mass. Molar mass of potassium dichromate is 294.18 grams per mole. So let's go ahead and set that up. We have 0.2 moles of potassium dichromate. We're going to multiply it by the molar mass. 1 mole of potassium dichromate is equal to 294.18 grams. Moles of potassium dichromate cancel out. We're going to get our answer in units of grams of potassium dichromate. Plug this into a calculator. We're going to get 58.8. And so the amount of solid potassium dichromate that needs to be weighed out to make this solution is 58.8 grams. And there we have it for problem 2. Let's go ahead and move into problem 3. Problem 3 reads, predict what will happen when the following pairs of solutions are mixed: potassium hydroxide and iron 3 nitrate. So let's go ahead and write this. Potassium hydroxide plus iron 3 nitrate are going to react to form what kind of products? Well, what's going to happen is that these ions are going to switch partners. So what we're going to form is potassium nitrate and iron 3 hydroxide. What is that going to look like? That's going to look like KNO3 plus iron 3 hydroxide. The next part of this problem that we need to do is figure out if these products are soluble or insoluble. If something is insoluble, then it is going to precipitate out. So let's look at potassium nitrate first. Potassium is a group 1 cation. Group 1 cations are always soluble. Also, if we look at nitrate, nitrate is also always soluble. So potassium nitrate is soluble, it will not precipitate out. Now let's look at iron 3 hydroxide. Metal hydroxides, they're insoluble unless they're paired with a group 1 cation or potassium, strontium, or barium. What we notice here for iron 3 hydroxide is iron is none of those options. And so indeed, this metal hydroxide is insoluble, and this product is going to precipitate out. Now, this is going to transition really nicely into the next problem. Example 4 says aqueous potassium hydroxide is mixed with aqueous iron 3 nitrate to form a precipitate of iron 3 hydroxide and aqueous potassium nitrate. Write the formula equation, the complete ionic equation, and the net ionic equation. So we already wrote this reaction. Here's one thing that we didn't do is balance it. So I'm going to write the balanced form. We covered balancing chemical equations in the previous chapter. So if you want a challenge or a reminder, pause the video, attempt to balance the equation, and then unpause the video. And now I'm going to write the formula equation in its balanced form. What we have here is 3 potassium hydroxide reacts with iron 3 nitrate to give us 3 potassium nitrates and iron 3 hydroxide. Iron 3 hydroxide, and this is a solid. Okay. We have 3 potassium hydroxide plus iron 3 nitrate gives us 3 potassium nitrates plus iron 3 hydroxide. And iron 3 hydroxide, we said, is insoluble. It will precipitate out, hence why we assign it a solid, S. Everything else is an aqueous solution. And the problem here essentially gives you that information anyways. This is our formula equation. Formula equation. What we want to write next is our complete ionic equation. So everything that's soluble is going to be written in its individual ions. So potassium hydroxide is soluble. So we're going to write 3 potassium. All right, and I'm going to forego the aqueous here and the solids. We know how to assign that now that we've written our formula equation. We're going to write 3 potassium plus 3 hydroxide anions plus iron 3 plus, all right, plus 3 nitrate ions. This is going to give us 3 potassiums plus 3 nitrate ions plus iron 3 hydroxide. This is insoluble, so we do not write it as separated ions. Now that we have our complete ionic equation written, complete ionic equation, we can start to look at what ions appear on the reactant side and the product side. We want to remove those when we write our net ionic equation. For our net ionic equation, we want no spectator ions present. So looking at our complete ionic equation, 3 potassiums appear both in the reactants and the products. So we wouldn't want to write that in our final net ionic equation. Additionally, we have 3 nitrate ions in both the reactants and the products, so we can go ahead and get rid of those. What we're left with is 3 hydroxide ions, an iron 3 plus ion, and of course our insoluble precipitate iron 3 hydroxide. And so now when we write our complete ionic equation, when we write our net ionic equation from our complete ionic equation, it's going to look like 3 hydroxide ions, aqueous, plus iron 3 plus aqueous gives us iron 3 hydroxide solid. And that is our net ionic equation. And there we have it. We went ahead and we solved problem 4. Now we can move into problem 5. Problem 5 reads, calculate the mass of solid sodium chloride that must be added to 1.5 liters of a 0.1 molar silver nitrate solution to precipitate all the silver ions in the form of silver chloride. So what we have for this reaction is sodium chloride reacting with silver nitrate. Both of these are aqueous solutions, and they react to form sodium nitrate, which is insoluble, as well as silver chloride, which is also insoluble. So we have 2 solids here. Now, from our practice with net ionic equations, what we'll realize if we write the complete ionic equation and then try to write the net ionic equation, they're going to be exactly the same. Because on the reactant side, we have 2 soluble reactants for which we can write in ions, like so. And then on the product side, we have 2 insoluble products. And so if we're writing the complete ionic equation where we write everything that's soluble as separate ions and then attempt to remove spectator ions to write net ionic equation, we notice there are no spectator ions. Our complete ionic equation is equal to our net ionic equation. And this is important because part of this problem is figuring out the mass of solid sodium chloride that has to be added to our solution of silver nitrite that results in a solution that precipitates all of the silver ions to form silver chloride. And that means we're really focusing on the chloride, the silver, and the silver chloride part of our reaction. So we can just write the following net ionic equation for those species that we're focusing very heavily on. Chloride plus silver ions results in silver chloride solid. Okay, now in this case, we have to add enough chloride ions to react with all of the silver ions that are present. So the first thing we need to figure out is how many moles of silver ions are present in our 1.5 liters of a 0.1 molar silver nitrate solution. We're given the liters of silver nitrite solution. We're given the molarity of silver nitrite solution. Now, what this means is that we also have, by the way, we can equally and rightfully say that we actually have 0.1 molar silver concentration, and we have a 0.1 molar nitrate concentration. This is really important to recognize, right? This is soluble. It will dissociate into silver and nitrate. And so your concentration of this full compound is equivalent to you saying that that is the concentration of the separated ions. This is important because this allows us to calculate the moles of silver ions that are present in 1.5 liters of a 0.1 molar silver nitrate solution. And what we can write now is that Okay, we know molarity is equal to moles over liters of solution. We can solve for moles if we multiply molarity by liters. We have our molarity and we have our liters. We have a 1.5 liter solution multiplied by a 0.1 molar solution, and we're going to just focus on the silver ions here per 1 liter. Liters cancel out, and now we get our moles of silver. Our moles of silver are 0.150 moles of silver. Now, looking back at our reaction, this is a balanced reaction. What we notice is we have a 1-to-1 mole ratio between silver and chloride ions. So if we have present 0.15 moles of silver, then what we need is 0.15 moles of chloride. Because silver and chloride react in a 1-to-1 ratio, 0.15 mole of chloride ions and thus 0.15 moles of sodium chloride are required. All right, because we're not just adding chloride ions and we're adding it in the form of sodium chloride, which obviously dissociates. But that means that by convention, 0.15 moles of sodium chloride is needed. Hence where we get our needed 0.15 moles of chloride. With this information, now we can finally figure out the mass of solid sodium chloride that we need. And we can do this really easily by multiplying by molar mass to get the grams. 1 mole of sodium chloride is equal to 58.45 grams of sodium chloride. Moles of sodium chloride cancel out. We get our answer in grams of sodium chloride, and the answer is 8.77 grams of sodium chloride. We need 8.77 grams of sodium chloride to be added to 1.5 liters of 0.1 molar silver nitrate solution to precipitate all of the silver ions in the form of silver chloride. Now we know how much sodium chloride we need, hence how much chloride ions we will have to react with just the silver ions to precipitate fully in the form of silver chloride. All the chloride is going to react with all the silver to form the precipitate silver chloride. With that, we've completed problem 5. We can move into our last and final problem. Our final problem reads, what volume of a 0.1 molar hydrochloric acid solution is needed to neutralize 25 milliliters of 0.35 molar sodium hydroxide? So what we have here reacting is hydrochloric acid, which is a strong acid, reacting with sodium hydroxide, which is a strong base, to give us sodium chloride and liquid water. Now, what's really important for us to recognize is we have a reaction between a strong acid and a strong base. And in our lecture, we talked about how to write the net ionic equation for a strong acid, strong base reaction. It is H plus hydroxide ions gives us liquid water. This is really important because it tells us what's actually reacting in the solution, and it's going to help us solve this problem of the volume of 0.1 molar hydrochloric acid solution that's needed to neutralize our sodium hydroxide solution. So we have our net ionic equation. This is a balanced net ionic equation. We have this 1-to-1 mole ratio between hydrogen ions to hydroxide ions. Now, the next thing that we want to do is calculate the moles of reactants, hydrogen ions and hydroxide ions. Let's do this first for our hydroxide ions. We know that we have 25 milliliters of 0.35 molar sodium hydroxide. And so that means we can go ahead and calculate the moles of sodium hydroxide. We have 25 milliliters of sodium hydroxide. We want to first convert this to liters. 1,000 milliliters gives us 1 liter of sodium hydroxide. And now we can use our molarity to get rid of the units of liters and have only units of moles. So we have 0.35 moles of solute, that's sodium hydroxide, over 1 liter of solution. All right, that's our definition of molarity. We just expanded it here so that we can cancel out units of milliliter, cancel out units of liter, and get our answer in moles of sodium hydroxide. What we have is 8.75 times 10 to the minus 3 moles of sodium hydroxide. Now, we know what's really reacting are the hydrogen ions and the hydroxide ions. And this mole that we calculated, this is the moles also of just sodium ions and just hydroxide ions. So we can consequently write 8.75 times 10 to the minus 3 moles of hydroxide ions. And that's good. That's what we wanted to know. The moles of hydroxide ions. We also want to know the moles of hydrogen ions. Since this is a 1-to-1 mole ratio, then this becomes easy. We also just have 8.75 times 10 to the minus 3 moles of hydrogen ions. Now, what we can do is finally begin to figure out the volume of 0.1 molar hydrochloric acid solution we need. What we have is the molarity. We have the moles. All right, we have the molarity for hydrochloric acid. We have the moles of hydrogen ions. What we need to figure out is the volume. We can do this really easily because we know molarity is moles over volume, and molarity is moles over volume. Let me write that properly. All right, we have molarity, we have moles. We can go ahead and solve for volume by rearranging stuff. How are we going to rearrange stuff? Well, we can just move volume to the other side and move molarity over to the other side. And so now we have volume is equal to moles over molarity. All right, we have our moles, 8.75 times 10 to the minus 3 moles of hydrogen ions. We have the molarity of hydrochloric acid, which is also similarly the molarity of just hydrogen ions. This is 0.1 moles of hydrogen ions over 1 liter. All right, and now if we calculate this, what we get for our volume is 8.75 times 10 to the minus 2 liters. All right, that is the volume of 0.1 molar hydrochloric acid solution that's required to neutralize 25 milliliters of a 0.35 molar sodium hydroxide solution. And with that, we've completed all our practice problems for chapter 4. I really hope this was helpful. If you have any questions, comments, concerns, leave them down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.